Howdy folks, welcome back. Today we're going to cover section 4 of chapter 6, and in this section the focus is going to be on rhombi. That's the plural of rhombus instead of saying rhombuses. And in a rhombus, by the way, it's a quadrilateral that has all 4 equal sides. And as you can see in our family tree, that the rhombus falls under the parallelogram. So anything that was true about parallelograms is also true about a rhombus. And it also, of course, falls under quadrilateral. The other shape that we're going to group together in this same section, though, is the square. The square, you might say, is the ultimate quadrilateral. It has all of these characteristics of the rectangle, the rhombus, the parallelogram. So like the rhombus, it has all equal sides. Like the rectangle, it has all right angles. And like a parallelogram, it has opposite sides that are parallel. So when we talk about squares, remember then that anything that applies to any and all parallelograms, rectangles, or rhombi also apply to squares. Okay, whereas the rhombus, the only other ones that apply to a rhombus would be ideas that we've already learned about the parallelogram. All right, so on the flip side here, I already have the definitions of each of those 2 shapes. The rhombus, as I said, is going to be a quadrilateral with all 4 congruent sides. Years ago, somebody once in my class said that a rhombus looks like an abused square, like somebody shoved a square off at an angle. Okay, the square then, on the other hand, is a step further than the rhombus. It also has, though, the 4 congruent sides, but it should also have 4 right angles. Okay, so I'm going to give you some theorems in this section as well. And the theorems that I want to show you here are all theorems that will apply to all rhombi, including squares then, because a square is a type of rhombus. Okay, so to give me some room for these theorems, I got 3 of them to write up here. I'm going to go ahead and erase this now. And I'm going to put up here then our first theorem, which is theorem 611. And in that theorem, if you look on your postulates and theorems for this chapter, it states that the diagonals of a rhombus are perpendicular. Okay, so to kind of give you caveman talk here, it says basically, if rhombus, then we'll use the same picture here over and over again for our rhombus here, but so I'll draw one over here. So we'll call this one A, B, C, D. Okay, but if that's a rhombus, then the diagonals AC and BD are going to be perpendicular to one another. Okay, so we know that they're going to form a right angle there. Okay, but that's theorem 611. Now theorem 612 is our next theorem on our list. And in theorem 612, it's basically the converse of this idea. Although like parallelograms, when we did a converse on those, or I should say the rectangle, in fact. But when we did our converse on that section as well, it's not a true converse. You can't just say if the diagonals are perpendicular, then it'll be a rhombus. Because after all, look at a picture like this one. If I make these 2 be perpendicular to each other and I connect this, you'll notice that this is not a rhombus. In fact, there's a kite, okay, instead of a rhombus. So it's not enough just to reverse this idea. Instead, on theorem 612, we do have to have perpendicular diagonals, but it also already has to be a parallelogram. So we're going to say if it's a parallelogram and AC is perpendicular to BD. Okay, because that would alleviate, like say the issue of the kite here, for example. If I'd already known from the get-go it was a parallelogram, then we wouldn't be able to make that shape. But if it's a parallelogram and the diagonals are perpendicular, then it's a rhombus. Okay, so that's theorem 612. And again, these two are just really the converse of one another. Okay, there is another theorem, theorem 613, that also applies to rhombi, rhombuses. And in theorem 613, it states that each of the diagonals of a rhombus bisect the pairs of opposite angles. Okay, so this one, it's kind of hard to give you a short caveman talk version of this one, but here's all it's really saying, according to theorem 613, is that if that's a rhombus, here we'll start out with, if rhombus, then, and I'm just going to write these then in this pink color, then it bisects, those diagonals bisect the angles. So like, for example, see this diagonal BD? It's going to split the overall angle D here into two equal halves. So that half will match that half. Now don't forget, in a rhombus, which is also a type of parallelogram, the opposite angles already match in the first place. So that means over here at B, we have again two matching angles that match these two. So all four of those will match. Okay, we could say the same is true at A and at C. Only instead of matching these four, they're going to be four other angles that match, but not necessarily these. Okay, so I'm going to mark them with double arcs. Here, there, here, and there. But all four of those angles match as well. Okay, so in the end, if we mark everything we know about a rhombus, including these new ideas in this parallelogram, there's actually all kinds of parts that are congruent in a rhombus. Since a rhombus is a type of parallelogram, don't forget what's true about a parallelogram, that those diagonals bisect one another. So that means this length here matches that length, and this length matches that length. So we got single, single, double, double. And by definition, a rhombus already has all four equal sides. So I know that this matches this, matches this, matches this. Okay, and of course, if that's a right angle, do you understand that all four of these are actually right angles? So a rhombus, you could say, then really breaks down into four different right triangles that are all congruent to each other. You can see we can prove all those triangles congruent by SSS or SAS, ASA, AAS, even HL. You know, all of those old shortcuts that we had, all five of those shortcuts, any one of them can be used. You could even use literally the definition of congruent triangles, which would be to show that all the parts match, all the sides, all the angles, because they do. Okay, all four of those triangles all match. You might say that each triangle just keeps being reflected or flipped over. So you can flip that one to there, take this one, flip it to there, take that one, flip it to there. Or you can look at it as rotations. This one rotates to there, and that one to there. Okay, there's all kinds of ways of looking at it. But regardless, a lot of congruent parts in a rhombus. And remember again, all of these apply to squares as well, because a square is a type of rhombus. All right, so there's our theorems for this section. Now I want to jump into some problems here. And the first of our problems, well, let me make a drawing here that we can refer back to then. And I'm just going to kind of leave that picture up there in the corner as a reminder that there's all kinds of congruent parts. Okay? So when I go to draw my next rhombus here for our first problem, I'm going to call this one P, L, A, N, and then where they meet here in the middle is E. So it's plane, P-L-A-N-E, plane. But anyways, in this picture here, P-L-A-N, I'm just going to tell you is a rhombus, okay? So plan is a rhombus. All right, so a few questions that I might ask you might be something like this. I might say, all right, take a look up here at triangle PLA. And I might ask you then, what type of triangle is triangle PLA? You know, what do you know for sure that you could say is true about that triangle PLA? Okay, if you look up here, you'll notice that PLA is that entire triangle right there. Okay, and if I kind of look back over here at our other rhombus, again, there is stuff that we can mark congruent here. Since it is a rhombus, I know that all four sides matched. So in my triangle here, now be careful, don't assume this diagonal length matches those. It kind of looks like it in my picture, but we can't assume that. Okay, but I do know that all the opposite sides match. So then this triangle PLA, I can say for certain then has at least two matching sides, which then of course makes it a, or I should say an, isosceles triangle. So triangle PLA is isosceles. We'll just put it like that, is isosceles. All right, now what if I had you focus instead on triangle PEN? Okay, triangle PEN, if you look up here, PEN is that part right there. Okay, on that part right there of the triangle of the rhombus is just one of those four triangles that we mentioned back over here again earlier that were all congruent. But more importantly, in here, if I wanted to try to be able to classify the triangle, I could see that it's going to have a right angle in it. It's going to have a right angle right there. So I could say that triangle PEN is for sure is a right triangle. Okay, so a couple of classifications of triangles there based on our picture. Okay, my next question that I might ask based on our picture here is whether or not triangle PEN that we just got done looking at, I want to know, is it congruent to triangle AEL? Is triangle PEN congruent to AEL? Now AEL, as you can see then, is the other triangle created right there. So the two green ones now is what I'm trying to focus on here. And just like we had indicated over here, not only are those two congruent, but all four of those triangles are congruent there. We could always prove it because of the idea that not only are all the sides the same on a rhombus, but the diagonals cut each other in half. So I know that matches that, and this matches this. So that's enough right there by SSS to show the triangle is congruent, or even SAS using the right angle. You could even use HL, you know, with the being a right triangle. So there's plenty of ways to prove this, but of course our answer then here is yes. Yes, they are congruent. Okay, something else that I might ask you in this picture. Is segment PA congruent to segment NL? PA, you can see, is this full diagonal. NL is that full diagonal. Okay, and I want to know if they're congruent. That might be true in a rectangle, for example, but that is not necessarily true in this case in a rhombus. Okay, a rhombus, when it comes to the diagonals of a rhombus, its diagonals are a lot like just your basic parallelogram. Single, single, double, double, you know, where you have some matching parts, but the overall length, if you add this single plus single here and you add this double plus double there, their overall lengths are not going to match. You can kind of see it, you know, if you let your gut instinct kind of guide you here. You can see that this one, this full diagonal PA, is a little bit shorter, because if I go over here, see how that one's longer? Okay, so no, these are not congruent on this one, and don't assume that they are. Okay, again, on a rectangle they are, but not on a rhombus. Okay, you could say they're the same on a square, because a square is a type of rectangle. All right, so let's try a few more problems here yet. I'm going to start with, again, a new picture of a rhombus. And on these next few problems, I'm going to have you find some measurements on these, instead of just, you know, yes or no questions like those were classifying triangles. All right, so I'm going to, again, start out with a new picture here of, again, a rhombus. Okay, this one I'm going to call ST VR, and then where these diagonals meet in the middle here, we'll call that point W. Okay, and again, STVR is a rhombus. Okay, so any and all of this stuff that we learned about a rhombus is going to be true. All right, so on our first question here, if I told you that the measure of angle RST is 67 degrees, let's make it, then I want to see if you can find for me the measure of angle RSW. Okay, the original angle given, RST, is this overall angle there. Okay, so I'm telling you that that overall angle is 67 degrees. And the angle I want to find, RSW, as you can see then, is only this part. Okay, and remember, we learned today in this section that on a rhombus, when you draw the diagonals in, it bisects the angle. It cuts it into two equal halves. So the angle they want us to find, RSW here, should be exactly half of that overall angle. So all I have to do then is take 67 divided by 2, and half of that then would be, what is it, 33.5. So there's what angle RSW would be. Half of 67, or 33.5 degrees. Okay, let's try another one here. This time, let's say that I'm going to give you angle STV as being 135 degrees. And I ask you to then find the measure of angle SVT. Okay, so this time let's ignore that 67 there. That was from our last problem. This time though, STV, which is this overall angle across there, is going to be 135 degrees, 135, and SVT though is this angle down here. Okay, so it's a little different than our last problem, but if I wanted to find that angle, I notice it's a part of this smaller little triangle, which I know from what I've learned today about rhombi. I already know that right here at W right there is a right angle. So I know that's 90. I know that this part right from there to there, that angle, is going to be exactly half of the overall angle, 135. So like I did over here, I do need to do half of the 135 to get this angle up here. And that gives us, let's see, 50 plus 15, 65, 67 and a half. Okay, so that's 67 and a half. I'm going to erase this 135 for now so you don't get confused, but that's 67 and a half degrees for that angle. And do you see where I'm going now? If I want to find this last angle over here, I know all three of those should add up to 180 in any triangle. So I'm going to take 90 plus 67.5. I'm going to add those together and see what that gives me. That gives me 157 and a half. I'm going to take that away from 180 to find our last angle now. So 157 and a half away from 180 is going to leave us with, oh, let's see here, 10, let's see, 22 and a half. Yeah. So 22 and a half degrees is what that last angle SVT right down here in this corner has to be. Okay? There was other ways to get that too. I mean, you could look at it as one big isosceles triangle, and we could have took the 135 away from 180 and split the difference between those two angles. You know, because remember we just talked about that earlier. These are isosceles triangles if two of the sides match, whether it be these two or those two, depending on how you look at it. All right, so you'll have problems like that where I'll have you find some missing angles. On our next one here, I'm going to make this into now an algebra type of problem. So let me clear up some space here. All right, and we can get rid of that 67 and a half I wrote up here, so that now you can just focus on our new algebra problem here. And let's see here. It's suppose the measure of angle SWT was given as being 2x plus 8. And I said, all right, if that's true, find x. Well, SWT, if you look carefully up here, SWT is that angle right there, which, as you can see from the marking I left from our last problem, as you can see, it'll have to be a right angle, actually. So all we have to do on this one is just simply say that 2x plus 8 equals 90. Equals a right angle. So I'm going to subtract 8, divide by the 2, and we find that x is 41. Okay, so there's a nice easy one. If they give you the right angle, one of the right angles set equal to 90, and solve for x. Okay, but the algebra problems could get, you know, a little more difficult than that. What if, for example, on our next problem here, what if I told you that angle WRV is equal to 5x plus 5? And suppose I also told you that angle WRS is equal to 7x minus 19. And this time I want you to find x again. Okay, so if you look at, again, the order of the letters for the angles they name here, the first one, WRV. WRV is that angle right there. WRS. WRS is the other one right beside it here. And don't forget, on a rhombus, those two in the same corner here like this are going to always be equal because the diagonal itself always bisects the angle. Okay, so the 5x plus 5 was this one. The 7x minus 19 was that one. And as you can see from my markings, they should be equal to each other. So that's exactly what I'm going to do for my equation. I'm just going to say that 5x plus 5 equals 7x minus 19 and solve for x. So in this case, I got a Sheriff Bandit situation. I'm going to get rid of the weaker one, so I'm going to subtract the 5x from both sides, leaving us with 5 equals 2x minus 19. Now I'm going to add the 19 over to the other side. So now I've got 2x equals 24. And of course divide by 2 to find that in this case x is 12. Okay? You could always plug that back in to actually find the measure of the angle as well. So if I plug that 12 back into here, or even here, since they're equal to each other, I can see how big that angle comes out to be. Okay, so those are some of the types of problems you'll run into on your homework. Now there's one other last type of problem here that I want to show you. But before I do, I want to kind of go back to your notes here and take some more notes on this last idea. Okay, and this last thing I want to show you is something that, well, is going to go back to all the previous shapes we've covered so far, really, in this chapter. If you remember correctly, one of the first shapes, other than just a basic quadrilateral, one of the first shapes we covered was the parallelogram. Let's see here how I want to keep my notes on this. We'll do this. Okay, there. Here's just a little parallelogram, a little picture one. And what I'm about to show you is something that's unique about the diagonals of each of these shapes. It turns out, you know, I've been showing you all kinds of methods to prove whether a figure is a parallelogram or a rectangle. Okay, and today I'm going to show you some techniques we can use just by looking at diagonals to determine whether it's a parallelogram, a rectangle, or even a rhombus or a square. So all four of those shapes are going to apply here. So we have the parallelogram that we've covered. We had the rectangle was the next one that we covered. Okay, and then today we covered rhombus and square. And actually, come to think of it, let's do this. You know, I'm going to draw this kind of like we did my family tree that I have on the other side of this board. Okay, I'm gonna draw it like that, where we had the parallelogram, and remember the family tree branched out to the rectangle and the rhombus. Okay, and then the square in our family tree, if you think of it like a real family tree, this is kind of gross, because this would be a product of a rhombus and a rectangle getting together and making a square, but the square then is both of those. Okay, and when we look at their diagonals, every one of these shapes has something unique about their diagonals. Okay, the diagonals of a parallelogram. Remember what was true about them? As you draw those, did you notice, remember, like we talked about before, the diagonals will cut each other in half or bisect one another. Okay, and how do we check for that if I'm giving you coordinates? You know, if I gave you points all along here and I give you coordinates, you know, like for example, if I said, oh, the coordinates here is 2, 3, and I gave you all four of those, for example, all those coordinates. Do you remember how we checked for if they bisect each other? Okay, if you said, hey, midpoints, you're correct. Okay, so on a parallelogram, we should be checking the midpoints. Okay, the midpoints are how we determine, because if they share that same midpoint right in the middle, for both diagonals, then that means they bisected each other. Okay, so these problems are going to be like that, where I give you coordinates. Okay, so again, if I gave you all the coordinates of the vertices here of this rectangle, let's see, yeah, we'll just put there, rectangle. Okay, do you remember how we would check? Now let's suppose that I already checked midpoints. Okay, this would always be on our list of order of things to do. This will always be the first thing we're going to check for. Okay, because if it passes this test, then I know it's at least a parallelogram. And now I'm going to work my way down the family tree. Okay, so this test right here for a rectangle, I'm going to call it my 2A test. And then over here, this one is going to be my 2B test. Either one could be your second test. That's why I'm calling it 2A and 2B. Because if I were to follow either path down, that would be my second test. So let's say I did test for the rectangle. Now remember, the diagonals of a rectangle, like any other parallelogram, are going to bisect each other. But in addition, remember that the diagonals of a rectangle are congruent. The overall lengths are congruent. So instead of single, single, double, double, if you remember right on a rectangle, we had single, 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 single all the way around. So let's say it already passed the midpoints. I already know they bisect. So in addition to that, for the rectangle, now I would check their distances, the overall lengths of the whole full diagonal. So in parentheses here, I'm going to put distance for that one. So if it passes that test, we check for maybe the distance now to see if it's a rectangle. In addition, then on this side of the family, then we have the rhombus. Now on the rhombus, do you remember what we just learned today is unique about its diagonals? Well, like any other parallelogram, they do bisect. So I do have, single, single, double, double, but not like the rectangle though. They're going to be different lengths overall. Okay, but there was one other thing that we could check for here, and that would be on a rhombus whether or not these form a right angle. Okay, they should be perpendicular as well. And you remember how we check for whether things are perpendicular, whether they form a right angle? If you said slopes, you guessed it right. Okay, we would check the slopes on that one. Okay, now, our last shape, the square. Now, keep in mind, the square qualifies as all of these shapes. It's a rhombus, it's a rectangle, it's a parallelogram. So its diagonals should do everything that these do. For example, the diagonals bisect each other, but in addition, they're also congruent. So it's like a rectangle where you have single, 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 single. You'll have the same thing here. Single, 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 single. Okay, so that's why it has that relationship, sharing that with a rectangle. But it also then falls under the rhombus as well. So it would also have that right angle here in the center where the two diagonals meet. So it's a merging of the two ideas. It's the single, 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 and the right angle of that one. Okay, so if I was testing to see what shape I have, to be a square just means that it would have to pass all three tests. Okay, so it just simply has to pass all three of the previous tests up here. The 1, the 2A, and the 2B. Okay? So again, to show you what I mean on these problems, let's do a few of these together so that hopefully you start to catch on. I'm going to start out with a figure that we're going to call Park, P-A-R-K. And in that figure, I'm going to give you the coordinates of P, A, R, and K. Let's say that P is located at -1, 0. And A is located at 1, -1. And R is located at 2, 1. And K at 0, 2. So there's our coordinates. I'm not going to sit here and graph this, although if you did make a quick sketch, it might give you an idea of what possible shape it might be. But I do not want you guessing. I want you to check. I want you to go through each of these tests to figure out what shape this is going to be. Now again, your first test should always be this one, because if it fails the parallelogram test, meaning it's not a parallelogram, then it can't be any of these shapes. So you always want to do that first. So we always want to check our midpoints first here. Now again, we're talking about the diagonals on all these. So it's the midpoints of the diagonals. So a figure called PARK, if I just make any kind of rough sketch of a parallelogram and go around in that order, PARK, I hope you see then that AK and PR are always the diagonals. Every other letter, PR and AK. So PR and AK are the two midpoints I need to find. Okay, don't forget to find a midpoint. We're averaging the X values and averaging the Y values. Okay, and that's our new X and Y values. So that's what I'm going to do here. For P, I've got -1. For R, my X value is 2. So I'm averaging together -1 and 2. And for the Y values, 0 and 1 is what I'm averaging. Well, -1 plus 2 is +1. Divided by 2 is 1/2, or 0.5. And 0 plus 1 is 1. Divided by 2 is, again, 1/2. So it turns out my X and my Y coordinate are both 1/2. Okay, let's do the same for AK and see if we get a match. Remember, if we don't get a match, then it's not a parallelogram, and it's none of these. So if it fails this test, we can stop there. Okay, but let's see what happens for AK. For A, my X value is 1. For K, it's 0, so I'm averaging together 1 and 0. For my Y values, -1 and 2 is what I want to average together. All right, 1 plus 0 is 1. Divided by 2 is 1/2. -1 plus 2 is +1. 1 divided by 2 is 1/2. So far, it has passed the midpoint test. Okay, so I could say that this is at least a parallelogram. All right, so my next step then is to go down and do one of these two tests. Now, I call them 2A and 2B because you can do them in either order. Okay, so they're both step 2s. They're both the second test you should do, but I don't care what order you do them in. I'm just going to go ahead and do 2A first. So in this one now, for a rectangle, if I want to see if it is a rectangle, I check the distance of the diagonals. Okay, so we're going to have to find distance of these same two sides, PR and AK. Again, if you forget the distance formula, it's that one big long square root, where it's the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, so on this one here, let's see if I can do this. Let me grab my calculator. Okay, if you have your distance program on your calculator, that always speeds things up. So, why do things the hard way here? I might as well use the same formula for mine as well. So PR, I'm going to put in the coordinates -1, 0. -1, 0. And for R, 2, 1. Okay, that tells me its distance is 3.16 approximately. Okay, now let's do AK and see if we get the same distance. If it's a match, I know it's a rectangle. All right, so for AK, I'm going to put in the coordinates 1, -1. And for K, 0, 2. Oh, what do you know? It's a match. I get the same distance for both of those. Okay, so now I know it's passed this test as well. So not only is it a parallelogram, now I know it's a rectangle. Okay, now don't stop there though. You still need to test for rhombus because it still has a chance it could be that. Okay, now to check for whether or not it's a rhombus, we have to find slopes of the diagonals. We're checking to see if they're perpendicular, if they form a right angle. Okay, and remember to find slope, it's just change in y, so y2 minus y1 on top, over change in x, x1 or x2 minus x1. It's important you go in the same order for both, and you put y values on top. All right, so PR slope. Okay, on top, I'm going to subtract 0 minus 1. On bottom, -1 minus 2. That's the slope of -1 over -3, but a negative over negative is really just positive. So that's positive 1/3 slope. Okay, we do the same for AK. So on top, I'm going to take -1 minus 2. On bottom, I'm going to go 1 minus 0 for the x values. That gives me a -3 on top, a +1 on bottom. And if you're thinking right now, oh, it doesn't check. Yes, it does. Yes, it does. Remember, we're checking for a right angle. And for slopes to form a right angle, remember one slope is going to be running in an uphill fashion, the other one in a downhill fashion, which means one should be positive, one should be negative. And remember, they should be the reciprocal of one another. So instead of 1/3, this one's 3/1. So they're the opposite sign and reciprocal, which means it checks. So it checks for that test as well. So our figure is a parallelogram, it's a rectangle, it's a rhombus, it's all three. It passed all three. So technically, it's a square. This turns out to be a square for this one. Okay, that's a square. Okay, if it passes all three, that's a square. Okay, now let's try another one of these just to show you, at least one more of these, maybe two, to show you then how it doesn't always end up being a square like that, you know. So let me give you some new values here. And again, we're going to do those same steps again. We're going to find midpoints and always check for that first. Remember, midpoints first. And then you can always go on and check the other two tests for slopes and distance. All right, so let's say on this next one, P has coordinates of 2, 11. A has coordinates of -3, 1. And R is 8, 3. K is 13, 3. Okay, first test that we should do then. I should get rid of these check marks. We don't know if it's past these yet, so that was from last problem. All right, so we check our midpoints of the diagonals. Again, remember the diagonals are PR and AK. So PR and AK are the two we have to find the midpoints of. All right, P, X coordinate is 2, R is 8, so 2 plus 8 divided by 2. We do the same with the Y values. 11 plus 3 divided by 2. Well, that's 10. 10 divided by 2 is 5. That's 14 divided by 2 is 7. So 5, 7 was our midpoint of PR. Now let's check AK. -3 and 13 are the two I want to average together for the X values. And 1 and 3 are the two I want to average together for the Y values. Well, -3 plus 13 is 10. 10 divided by 2 is 5. 1 plus 3 is 4. 4 divided by 2, though, is only 2. Notice the mismatch. 5, 7, 5, 2. That's not a match. So it failed this test. So that means it's not a parallelogram, and there's no need to do any other tests here, because if it's not a parallelogram, how could it possibly be any of these other shapes which fall under the parallelograms? So in this case, if you were to graph those points, it would not make any special quadrilateral. It would just be a basic looking quadrilateral, you know, maybe something like that. Okay, it doesn't make any special shape though. Okay, so there's that problem already. That's just a basic quadrilateral. Okay, let's try one more of those then, since that one went so fast. And I'll try to give you one that turns out to a different shape this time. Let's say that P this time is given the coordinates of -1, 4. A is at -1, 10. R is at 14, 10. And K is at 14, 4. Again, I always want to do that test first. See if it's a parallelogram to begin with. Okay, so we're going to check the midpoints of the diagonals, PR and AK. Alright, for P, -1, R has 14 for an X value, so I'm going to add those and divide by 2. For the Y values, 4 and 10 get averaged together. Well, -1 plus 14 is 13. Half of 13 is 6.5. 4 plus 10 is 14. Divided by 2 is 7. So 6.5, 7 are the coordinates of the midpoint of PR. Let's see if we get the same for AK. So I start with my X values, -1 and 14. I'm going to average those. 10 and 4 are the Y values that I'm going to average together. Well, -1 plus 14 is again 13 like above here, and half of 13 is 6.5. And 10 plus 4 is 14 just like up there. Divided by 2 is 7. So it's a match. Alright, so I know that it already passed this test now. It is a parallelogram. So at this point, you could follow either branch down your family tree, either test 2A or 2B. I'm going to just go ahead and do 2A next. So I'm going to check distance. Okay, we're going to find the distances, again, of the two diagonals, PR and AK. I'm going to take advantage of my calculator here to do those. So P had coordinates of -1, 4. If I enter that into my program along with the coordinates of R, 14, 10. My calculator tells me the distance on that one is 16.16 approximately, 16.16. Yeah, I'm going to do the same with AK. I'm going to enter my coordinates into my calculator and let my program do all the work. So -1, 10 and 14, 4 for K. And I get a match, 16.6 again. Okay, so that tells me that it passed the rectangle test. So now I know my figure is not only a parallelogram, but it's also a rectangle. Okay, so now we're going to go ahead and do our last test, the slopes. And I need my slopes to be perpendicular, so I don't want matching slopes. I want to remember complete opposites. Okay, I want them to be the one be positive, one be negative, and I need them to be the reciprocal of one another. So I'm going to check the slopes of our diagonals. So for PR, I subtract my Y values on top, so I'm going to have 4 minus 10 over -1 minus 14. That gives me -6 over -15. And a negative over a negative is really just a positive. That even reduces, by the way. 3 goes into both of those. So you could call this actually 2 over 5, positive 2/5. For AK, y values on top, so 10 minus 4. X values on bottom, negative 1 minus 14. Okay, that gives me a positive 6 on top, a negative 15 on bottom. Again, it does reduce, but it's not positive. You see how this was a negative over negative, which was positive? This is a positive over a negative, so it's negative, but it does reduce to the 2/5. Now, does that check? Does that pass the test? If you're saying yes, you're wrong. Because remember, not only do they need to be the opposite sign where one's positive and one's negative, but they do need to be the reciprocal of one another. You have to be able to flip it over. So instead of 2/5, this one down here needed to be like 5 over 2. So it failed that test. Okay, it failed this test. So if it passed this, but failed this, it's not a square, because squares have to pass all 3. It's not a rhombus. It's just a rectangle. See that? That was the highest test it passed. So I know that that figure is a rectangle. Okay? So these techniques that I'm showing you here, where you just have to check for the diagonals, the 2 midpoints, distances, and slopes, are really a lot less work than some of the stuff we did earlier. You're probably thinking, man, why didn't you show me this earlier, Mr. Hess? Well, I wanted you to be aware of all the possibilities, different ways that we could prove figures are different shapes. But this is a great way to show whether it's any one of these 4 shapes. So we only have 2, 4, 6 things to show, and you could show it's any one of these 4 shapes. Again, all based off of diagonals, okay? PR and AK. All right, that should be enough to prepare you for your homework assignment, which should be on pages 317 and 318. Problems 22 through 26 do evens only. On 28 through 37 do all of those. And 38 through 46 do the evens. Okay, and I'll catch you for our next lesson.